Hello everyone and welcome back. My name is Mr. Kovalt, and in this video I'm going to be going over the autoionization of water. So let's review a few things. First we want to review that water can act as an acid, and we saw that in an earlier video where we were reacting HCl, hydrochloric acid, with water. And the HCl, remember, is a strong acid, so it's going to dissociate completely, or I shouldn't say dissociate, I should say ionize completely, because this is a molecular substance. It's not an ionic substance. So these are not ions, but they will become ions in water. So they're going to ionize. And so water here is going to act as the base. And so it's going to act as, the base. So I have this backwards. So let me correct that right now. So this is acting as the base, and this is acting as the acid. Okay. So we know that water here is acting as the base because, according to the Bronsted-Lowry definition of base, it's a proton acceptor. So here's the proton donor. So HCl is going to donate a proton, or H plus, to water to make H3O plus, the hydronium ion, and then you have the anion left over. And again, this is a strong acid. So this is going to ionize completely in water, and so you get the one arrow going that way. So the equilibrium for this lies far to the right side, the product side. And here water acts as an acid in this case. So here we have a weak base, and that's going to react with water. And here, water is going to be the donator. So water is going to donate a proton, or H plus, to the ammonia, and you're going to get ammonium and H4 plus and the hydroxide ion left over. And so here, water is acting as an acid. So we're using the Bronsted-Lowry definition of acid and base here. So we said before that this means that water is an amphoteric substance. What does that mean? It means that water can act as an acid or base. Anything that's amphoteric can either act as an acid in one context or as a base in another context. And so because if you have pure water, right, so if water is just lying around and water molecules can act as acid or base, then it makes sense that if they're bumping into each other, then they can pass the proton to each other. And we call that the autoionization of water. So when you just have pure water by itself, it actually is not pure water. You don't simply have only water molecules floating around in your water. You actually have some acid and some base floating around there as well. So there's no such thing as pure water if we're thinking of only water molecules. So here you have the autoionization of water, where one water molecule is going to act as the base, where it's going to pick up the hydrogen and it's going to form the hydronium ion. And then you have the other water molecule that's going to donate the H plus, and so that's going to give rise to the hydroxide ion. And so this is acting as the acid. So we have this autoionization of water. So this leads us to a new dissociation constant, or equilibrium constant. So we talked about equilibrium constants for reactions. We called those the K values, right? And then in an earlier video, we talked about the equilibrium constant for acids, right? So we call those the Kas. We also later will be talking about Kb values, right? So the equilibrium constant for bases. But now we can talk about the equilibrium constant for the autoionization of water, and we call that Kw. And so here we have the Kw expression, and we call Kw either the ion product constant, right? So for water, the ion product constant, because we're taking the H plus ion and the hydroxide ion, the hydronium and the hydroxide ion, and we're multiplying them together. How did we get this equation? It's exactly the same way we get any equilibrium constant, right? So remember, if this is our equation, then the equilibrium constant is the ratio of the products over the reactants. Remember, it's the concentration of the products raised to the power of their coefficients, right? So if the coefficients are 2, then they're going to be raised to the power of 2. Divided by, on the bottom, you have the reactants, the concentration of the reactants. And remember, liquids and solids do not count because their concentrations do not change. They're constant. So here we have liquids. So the reactants, both reactants are liquids. So they're not going to find themselves in the equilibrium constant expression. So you'll notice that we have the concentration of H3O plus and the concentration of OH minus. Notice there's no coefficient. The coefficient, or I should say the exponent, is 1 because the coefficients are 1 here. Notice that there's no reactants on the bottom here. We just have the products because both reactants are liquid, so they're not going to be included in the equilibrium expression of the autoionization of water. So here is where we get the expression. So Kw is that autoionization, the equilibrium constant, and we call that the ion product constant for water. Or we also call it the dissociation constant because we have this, we can represent the equation of the autoionization of water like this. So we have H2O liquid that dissociates or ionizes into H plus and OH minus. And so we get this expression. So this is the expression for the dissociation constant for water. And so if this is our dissociation constant, now we can talk about how much H plus or OH minus do we have in water. And so we can figure out what the Kw for water, for the autoionization of water at 25 degrees or at any temperature. But since room temperature is typically 25 degrees, we know that water at 25 degrees is going to have a Kw of 1.0 times 10 to the 14. So because we know that Kw is equal to the H plus concentration multiplied by the OH minus concentration, we multiply those together. Since water is the only thing that's involved, if we have pure water, then when one water molecule donates a hydrogen to another water molecule, so this one's donating to this one, or this one's donating to this one, right? So since water is only involved, then we produce for every water molecule or 2 water molecules, we always produce 1 H3O plus, the hydronium ion, and 1 hydroxide ion. So we're always going to have equal amounts of both of these because they're produced in a 1-to-1 ratio. So that means that in pure water, the H plus concentration is always going to be equal to the OH minus concentration, and we can call that X, and we could plug X in for both of these, right? So now Kw is equal to H plus concentration multiplied by the OH minus concentration, and since both of these are X, that's going to be X times X gives us X squared. And so we know that X squared is equal to 1.0 times 10 to the negative 14. So we just take the square root of both sides, and we find that X is equal to 1.0 times 10 to the negative 7. So why is that important? Well, we can see that this is a very small number. So there is a tiny, tiny, tiny bit of OH minus and H plus in pure water. So it's not a whole lot, but it's there. And so this is always the case for pure water. Now, so when we're talking about H plus concentration, what happens when we add acid or a base to water? So the thing to remember is that at this temperature and always at this particular temperature, Kw is always equal to 1.0 times 10 to the negative 14. Just like any equilibrium constant, as long as the temperature is constant, the constant itself is constant. That was kind of strange that I just said that, but it's true. So at this temperature, this is constant. So it's always going to be 1.0 times 10 to the 14. So if we understand that, then if we change one, then the other changes in the opposite direction. If we increase the H plus concentration, then the OH plus the OH minus concentration has to decrease by the same factor. So if we double the amount of H plus, we need half the amount of OH minus, and vice versa. So, for example, let's say that our H plus, we throw some acid into our water and we raise the H plus concentration up to 1.0 times 10 to the negative 3, right? So if Kw and then we're assuming this is 25 degrees, if Kw is equal to 1.0 times 10 to the negative 14, and then that's going to be equal to H plus multiplied by the OH minus, and we just raise the H plus concentration to 1.0 times 10 to the negative 3, right? So then we multiply that's multiplied by the OH minus concentration. So we can solve this for OH minus. So we divide both sides by 1.0 times 10 to the negative 3, 1.0 times 10 to the negative 3, divide this by 1.0 times 10 to the negative 3, and we end up getting OH minus concentration is equal to 1.0 times 10 to the negative 11. So you could see that the H plus concentration, you could see that normally it's, what do we say, negative 7, right? 1.0 times 10 to the negative 7, but then we increase that by a factor of 10,000, right? So we increase that from negative 7 to negative 3, so that's an increase about 10,000. So this goes up, this decreases from negative 7 to negative 11. So that's a decrease by a factor of 10,000. So in acidic solution, we see that the H plus concentration is greater than the OH minus concentration. So that is true under acidic conditions, right? And these two multiplied together have to equal the constant, the dissociation constant of water at 25 degrees, if we're at 25 degrees. What if we take another example, what if it's a basic solution? Let's say we put some base in there, we increase the amount of OH minus, right? OH minus is a base. So we increase the amount of OH minus in our solution. So what happens there? So if we have, let's say we have 1.0 times 10 to the negative 2 OH minus concentration. So if we have Kw, that again is equal to 1.0, oops. Sorry about that, the light went out again. So back to this. So we have Kw is equal to 1.0 times 10 to, times 10 to the negative 14. And again, that's equal to H plus times OH minus. So we got H plus times the OH minus, and this time the OH minus concentration is 1.0 times 10 to the negative 2. So 1 times 10 to the negative 2. So this time we divide both sides by 1 times 10 to the negative 2, 1 times 10 to the negative 2. So here, this cancels out. And then here, the H plus concentration is equal to 1.0 times 10 to the negative 12. So you could see here that normally the OH minus concentration is negative 7, but we increase that by fivefold, right? I don't know if that's the right term, but we multiplied this by 10 5 times, right? So that's 100,000, right? So that's a factor of 100,000 that we increase the amount of OH minus right here. So our OH minus was increased by a factor of 100,000. And so that means that when we find our H plus, the H plus concentration was, oops, that should be a 12, not a 2. That our H plus concentration decreased by a factor of 100,000. So it went from -7 down to -12. So again, dividing this by 10 5 times, right? So what do we learn here? We learned in the basic solution, the H plus concentration is less than the OH minus concentration in basic solution. But again, when you multiply these together, these concentrations, they are always going to equal 1.0 times 10 to the negative 14 at this temperature. I hope this was helpful. I hope this was educational and interesting. And so if you like this video, please hit that like button right there, right there. And also make sure that you subscribe to my channel. Hit that notification bell so you'll be notified by other videos I put out. Please comment down below. Let me know what you think and if you have any other questions that I can answer. Thanks for joining me. Have a great day.